In this video, we're going to be taking a look at a banked curve problem where we're going to solve for an unknown angle of our ramp here. And if the car were going about 55 miles per hour and the radius of curvature is about 45 meters, what angle would help it sustain that circular path? So we're taking a look at the rear view of the car that is swooping around counterclockwise in a circular path. So if we take a look at the forces acting on it, we of course have the force of gravity straight down, and we have the normal force pushing up perpendicular from the surface. Now we're going to break those two into some components, and we have a vertical and horizontal component for our Fn, and we also have a perpendicular and parallel component for our Fg. Now, if we take a look at this theta over here, we can see how it translates. So this theta over here is in a 90-degree triangle. So here's my 90-degree angle right here. So that means this angle right here is the complement of this angle. And then that means this angle is the complement of that angle, which means this theta translates over here. And then these two are vertical angles to one another. So both of them actually contain this unknown theta. Now let's go ahead and write down some things that we know without doing too much mathematical stuff. So we know that the hypotenuse of this triangle is going to be mg, and then there's only a couple of vertical components going on in our picture here. We have this one straight down and then this one straight up. So this one must be the equal and opposite component because there is no movement in that vertical direction. And then we also know that this component over here is our Fc. That's our centripetal force. It's pointing towards the center of our circle. The center of our circle would be somewhere over here as the car swoops around in the counterclockwise direction. And we know that the centripetal force is equal to mv squared over r. Now, with that being said, we have a good triangle to work with over here, and we can use some sine and cosine components. So if we use the sine of theta, that's taking the opposite over the hypotenuse. The opposite end is our mv squared over r, and then our hypotenuse is that normal force. And then if we take a look at the cosine, then that's going to take our adjacent side, which is our mg. So that is our mg divided by the hypotenuse, which is also our Fn. So if we do a quick little cross multiply, then we could set this Fn equal to mv squared over r over sine theta, and then this Fn would equal mg over the cosine of theta. Okay, from there, you can set these two equal to one another. So you have mv squared over r over sine theta equals mg over cosine of theta. And what we can do is we can do a quick little cross multiply to sort of simplify our values and to get a single theta to solve for, because our unknown theta is the thing that we are focusing on as our final solution. So if we cross multiply those two, that leaves us with mv squared over r over mg, and then the sine theta is going to be above the cosine theta, which would make it tangent of theta. So then from there, our m's are actually going to drop out. And then since this r is below that v squared, it actually dropped into the denominator. And then our final expression is going to look like this. It's going to be v squared over g times r equals the tangent of theta. So now we have a nice little formula that we can work with, and then we can plug in our velocity and our radius and find our unknown theta. So we have our velocity of 25 squared over g, which is always 9.8, times our r value, and that equals the tangent of theta. When we take all of this over here, we're basically going to have to do the inverse tangent of this value over here, which comes out to about 1.42 rounded off, which means that our unknown theta is going to come out to about 54.8 degrees. Okay, obviously, that kind of incline is really, really extreme for a car to drive onto, but also cars typically don't go 55 miles per hour around a banked curve and expect to have no friction acting on them. That's why that angle ends up being pretty large. So to sum things up, you can use this formula over here. I just wanted to derive the formula to show you where it came from, but that's going to show you the unknown angle at which a car can swoop around in that circular path at a particular velocity and radius. I hope that was helpful to you. Thank you for watching and listening.